Good evening, everyone. So, today we will be starting this session shortly. We'll wait for some time so that everyone can join, and after that, we'll start this. So this week, yeah. So this week we will be starting with the week 11 content for the course OPAM Practical Applications, Design Simulation and Implementation. Just before going through the contents of week 11 and solving some questions, we'll just go through what we did in week 10. So in week 10, we we saw the application of analog multipliers. What are the analog multipliers? Like they are simply multiplying the input signals. Like the output is the product of the two input signals and divided by a scale factor. Then we saw that there are single quadrant, two quadrant, and four quadrant multipliers. We saw that also, and the regions and the voltage input which we can give to them, that also, we studied about that. Then we came to know about logarithmic multipliers, like which take log and then take anti-log to finally get the multiplication of the input to input signals, or we can get the division, like division this form also. Then we saw about the Gilbert cell and how this Gilbert cell can be used to realize the dual quadrant multiplier and as well as a four quadrant multiplier. Then we saw that how op-amps, how we can use these analog multipliers, the feedback of the op-amp, to get the divisions, to get to divide, to get the division operation, to do the division operation. And so we saw two configurations for the op-amps. And then Then we saw about the automatic gain controller, how the gain of the op amp will be constant, uh, irrespective of the input given, as it is because some part of the output is being feedback to the input signal and we use two analog multipliers so that our gain will remain constant. And then we saw about ADCs, analog, before that we saw that effect of like what is quantization errors, like it is maximum of plus minus half LSP, that is least significant bit. And then we solved some of the assignment questions and some extra questions also. And yeah, so this was all about the week 10 lecture. So there were questions on successive approximation and also dual slope ADCs. We talked about dual slope ADCs, counter type ADCs. Then yeah, so these were the content of the last week, and today we will be looking into week 11 content, in which we will be talking about DAC, that is data acquisition, digital to analog converters. Okay. So we'll be looking into DACs, that is DAC, that is digital to analog converters. So basically, in simple form, we can say we are giving digital signal to this thing DAC. Let's say it is of n bits, and we are getting some analog signal, continuous signal, we can say continuous analog signal. Okay, so the output of the DAC, if you talk about the output of DAC, it is basically given by some scaling factor k in multiplication with the reference voltage which we are giving to this DAC and the digital input. So in further we can write this as VFSR B1 B2 so on till Bn 2 to the power minus n. Okay, so what here we have done, this is the full scale range, the maximum value or maximum scale, the range of this DAC full scale range. This is uh, the digital input. This is MSP, the most significant bit, and this is the LSP, least significant bit. And values of B1 to Bn is 0 or 1, depending on like we know that digital inputs are either 0 or 1. So based on that, this B1 to Bn is 0 or 1. Okay, and n is number of bits. Number of bits. Now there are so this is one of the important equations for the DAC, so we can highlight this. Now uh, talking about some of the things about the DAC, DAC can range from 0 to VFSV, that is full scale value, And full scale value is given by 1 minus 2 to the power minus n divided by VFSR, full scale range. Another thing is the the most significant bit contribution to V naught. The output voltage is V full scale range value divided by 2. Okay, because we saw that this is the most significant bit and this is the contribution from that. And the least significant bit contribution, that is LSB contribution, is VFSL by 2 to the power n. By the magnitude also we can see that MSP is contributing the highest magnitude to the output of the DAC, and LSP is contributing the least magnitude to the output of the DAC. Then we have dynamic range as dynamic range 20 log, but these are just for like just for the these things are just for the information, just to like you should know some things about that. That's why like I'm telling these things. Okay, so now so if we, let's say we take an example of a 3-bit DAC. So we have this DAC, we have 3-bit means we have B0, B1, B2. There we are applying the V reference voltage and we are getting an output V0. Okay, so now we have this, that is 0 0 0 1 0 0 1 0 1 1 1 0 and 1 1 1. So these are the inputs which we can get from these three things: B0, B1, B0, B1, B2. Okay, so that is basically, or we can write B1, B2, B3. Since we have written here as from starting from B1, so we'll write from B1. So here also we'll write from B1. Avoid confusion. Uh, B1, B2, B3. Okay. So now another thing. So we can have 8 bars for this, like based on the resolution. So by the way, the resolution is given by V full scale range divided by 2 to the power n. So this is the resolution for 8-bit. We have, if we are saying that the reference voltage is 1 volt, then it will be 2 to the power 3, that is 1 by 8. It's the resolution. So the quantization levels will be at 1 by 8 steps to each other. So this is one quantization level. Another one is 2 by 8, then 3 by 8, 4 by 8, 5 by 8, 6 by 8, and 7 by 8. Okay. So when 0 0 came, so the output given by the DAC is 0. So how we'll understand this graph, this plot? So and when 0 0 1 came, we got an output of this 1 by 8. When 0 1 0 came, then we got an output of 2 by 8 at the output. For 0 1 1, similarly we got this. For 1 0 0, this one. Okay. For 1 0 1, it is this. Oh, sorry. For 1 1 0, and for 7 the last, we got this. So we have 8 bars for n equals to 3-bit. Okay, now so this is basically transfer characteristics for 3-bit DAC. 3-bit DAC. So this is the output, this was input, and we got based on their corresponding values, we got the output for that. Okay. So now we can observe this. Higher the n value, higher the n, that is number of bits, finer will be the resolution. Finer will be the resolution. And this figure, the figure which we just saw here, okay, this one. So this will be like, it will look more continuous. Okay, so it will be more continuous. One thing. Second, so now, the question can, then question will arise in our mind. So we can keep on increasing the n value, and then we can get as much good resolution as we want, and we can get a fully continuous wave. But it is not completely correct because uh, we have like DACs with 6, 8, 10, 12, and 14 bits. These are common and economical also. Economical. So if you'll keep on increasing the n bits above this, for n greater than 14, the tag become expensive. Okay, one thing. And also like the circuitry become called complex. Circuit is complex, so it needs proper care. So basically it is like difficult to handle such high resolution, high number of bit stack. And we can get our solutions with using which we can use these 14 bits and 12 bit stack like for our day-to-day purpose, and like for lab experiments and all. So we can go with till 14. 14 is also really good. So in 14 we have basically 2 to the power 14 number of uh, this levels, so it is really high. So LSP will be 1 upon 2 to the 14. So this is like based on the V reference voltage, it will be scaled, but still it is very less. So we will be having a very good resolution in 14 bit tag. So now just for the okay, so now I will tell you about this like, so we have two types of deck, basically two types of deck, two types of deck. Okay, so one is first one is weighted register DACs, and second one is R2R ladder DACs. So we'll see the circuit. And so if you talk about the weighted circuit DACs, weighted register DACs, or binary weighted, or we can say just weighted register DACs. So these are so I will make the circuitry using op amps and inverting amplifier circuit. So we have a reference voltage, we reference is then, so we have registers of in multiples of 2. So we have 2R, 4R, 8R, and so on till, so if you're talking about n bit DAC, this is n bit, so then it will be 2 to the power n r. Currents are IN, I3, I2, I1. and then we have a switch. From here, like our digital input will come from B1, B2, B3, and till Bn. This is Bn, and this the other part of the switch is connected to the inverting terminal of the op amp. So here we have the inverting terminal op amp having a feedback resistor of RF giving an output voltage V naught. The non-inverting terminal is being grounded there. So here we have AND switches. Here we have AND switches. So the output voltage is given by minus RF by R Vref. So this equation we saw earlier also, this one. So this was V naught equals to VFSR into V1 to the power minus 1 plus and so on. So same here we saw this equation. The only difference is that our VFSR, the full scale range value, is given by the multiplication of V reference voltage and the amplifying factor, that is the RF, the feedback resistor, and the R, the input resistor R. So there are like just for the like extra information, there are some, we have offset and gain errors in this type of DAC. So for that, like we can nullify these offset errors uh, by trimming the offset voltage, and also the gain error can be nullified by using the adjusting this RF value by adjusting RF. We can adjust the gain error and by like trimming the offset voltage, we offset, that is the offset voltage of the op amp, we can adjust the offset error. So these two are basically static type of errors. So we don't have to dig deeper into these kind of errors, as there are many, not many, but there are some, but it's not us for us to look into that. So but one more thing, like the drawback of this circuit is that they have these switching resistors. Like there are the resistors used here are, these are switching resistors. So even these switches which we are using here, they also contain some resistances. And if this resistance which is being used as in the switch, or we can say our switch, if this is compare in comparison to this 2R value, this 2R value, so it will if it load the it will load our circuit, our main op amp circuit. So this is one problem. Another problem is that these weighted resistors which we are using, we need in multiples of 2, that is 2 or 4 or 8 hour. But in practicality, we say, so these registers are not that perfect, so there are some tolerance values for these registers. So because of that, we cannot get the exact values of register as we want. So based on that, we'll be having some errors due to that, and that will be huge because we are going till n bits. So from starting from 2r to 2 to the power nr. So these are some of the drawbacks. So now if we talk about the R2R ladder circuit, R2R ladder. So then we have a reference voltage Vref. This is our, it goes till n bits, that is in the end it is R2R. We have 2R here, and then we have a switching circuitry, and then we have a switching circuitry for this, that is which will switch, so this will be switch based on the digital input which we are giving, b1, b2, b3, bn minus 1, bn, and we have, and the other and the this part is by default connected to this ground terminal, and the other part is, so these are two terminals. So one is connected to the inverting side of the op amp, and another one is non-inverting, and we are giving then a feedback resistor RF from this op amp feedback network and getting the output voltage V naught. Okay, so this is a typical R2R ladder circuit network. So it these so these this is basically a current mode network, current mode, because here we are like getting the current value like based on this network, and we are then finally out getting the output V naught. So here also V naught is given by minus RF by R into V reference. We reference the voltage given here, and then we have b1 to the minus 1 and so on till bn2 to the minus n. Okay, so this is the output voltage of the stack. So this is the thing. So so we saw that there are two types of DAC. One is weighted resistor DAC and R2R ladder DACs. So weighted resistor DACs, they use multiples of two multiples of these resistances, that is 2R, 4R, 8R, and so on, 2 to the power nr. And then we saw about this the output voltage equation for them, and then we saw also this R2R ladder, which is again, but in R2R ladder we are only using R and 2R resistance circuits as the resistors in our circuit. So because the drawback which we saw in this weighted resistor, that it is difficult to get these like different values of resistance, exact value of these different resistances in practical life, then that's why we went for this R2R. So it is comparatively easy to achieve this circuit. So that's why it overcomes that drawback of the weighted resistor attacks. So this was a brief overview of the stack, and we'll start with solving some questions. So first of all, I will. So if you have any doubts, you can ask. Otherwise, anyway, I will start with the questions. So I'll solve each and every question, like not completely, but yeah, I'll give you hints. So yeah, question one. So dash type of DAC requires two set of resistors. So as we just saw, and the name also suggests, like in the name itself, it is given which is using two set of resistors. So we can answer this question. So this is easy. Then we have Dash type of DAC utilizes summing amplifier configuration. So summing amplifier configuration, if we see, then if we see this binary weighted DAC, then it is something like this. If it's go for 4 bit, let's say 2k, 1k, 3k, 4k. So these all are being summed together and being given to this op amp. We have some RF. This is V output. This is VA, VB, CVD. So this is an example of a summing amplifier. Okay. So this is uh, so we can see that, okay, summing amplifier is being used in binary weighted DACs. So this is also, I think, okay. So conversion rate of DACs. So this is a fact-based question. You can answer like by referring to some textbooks. So this also like I think you don't have any problem in this. Then next question. Let an input to a 5-bit DAC is, okay. We have a 5-bit DAC and input is 0 0 0 0 1. And the corresponding output is zero point 0.2 volts. So for this we have a zero point 0.2 volt output, and compute the output of DAC for an input of, so now if we have 1 1 1 1, so what will be the output? So this is also, I think, easy. So we have this formula, the resolution equals to uh, V full scale range divided by 2 to the power n. So here like the resolution is zero point 0.2 volt. Why it is zero point 0.2 volts? Because this is the least significant value which we can input to the this one, which measurable is significant value which we can input to the DAC, that is 0 0 0 1. So corresponding output will be its resolution. So 0 0.2 is equals to, we have 1 to the 2 to the power 5 n bit, it is n bit, so it is this. So we have VFSR. Okay, now we have the value of VFSR as 0 0.2 into 2 to the power 5 equals to VFSR, this one. So based on this we can calculate the value, what will be the value for this. So we know the output equation for this DAC, that is VFSR into 2 to the power minus 1 B1 plus this 2 to minus n Bn. So we have 5-bit DAC, so it will be 0.2 into 2 to the power 5 1 by 2 into B1. So B1 is what, 1 plus 1 into 1 by 4 plus 1 into 1 by 8 plus 1 into 1 by 16 plus 1 into 1 by 32. 1 2 3 4 5, yes. So if we solve this, so we'll get so we can get the answer if we solve this. So this is also okay, easy question. So now next question. In continuation to the previous problem, determine the output for the of the DAC for an input of 10001. So now we have to use the same problem. So we not, now it is easy, I think. So we have VFSR value, that is zero point 0.2 into 2 to the power 5, and we have one at the MSB and one at the LSB. So based on that, the B1 and the B fifth component will be 1 here in this case. So 1 into 1 by 2 plus everything in between will be 0, 1 2 3 4 plus, and the last bit will be also 1. Okay, so based on this we can also derive the answer for this question. So this is also easy. Now the next question. Compute the percentage resolution for a 10-bit DAC having a step size of 2 millivolt. So this percentage resolution a term has have came here, and they are saying to solve it for 10-bit DAC, and they have given a step size of 2 millivolt. So basically the step size is the resolution. Is resolution what it is the same meaning as as that of resolution. The resolution is also the same thing. So it is given that it is 2 millivolt. So again, so basically percentage resolution is the resolution divided by the full scale value into 100. So now we have resolution which is equals to 2 millivolt. We also know the full scale value, full scale range, we can say this range divided by what, 2 to the power, and n is 10. So we have full scale range we can get from this value, from this function. So it will be percentage resolution will be then equals to, this will be 2 milli into 2 to the power 10 divided by full scale range, that is uh, okay, sorry, this is 2 milli into 2 to the power 10 at the denominator, because FSR value is this one. So from this equation we have got the expression for VFSR, and for VFSR being we have used this VFSR in the percentage resolution formula. So this will be like, if you solve this you will get the answer. So this is also, I think, okay. So now the next question: digital to analog converter converts binary word to a. So we have seen in this also, I've told, yeah, this this is a current mode. So basically it is converting the final output into a current, which we are finally getting into terms of voltage. But we have voltage mode 12 letters also. So similarly we have like voltage or current mode DACs. So based on that, we will be getting an output in terms of current or voltage, depending on our output circuit. So these are two the main or fundamental values which we can get from the DAC, output of the DAC. So this is also okay. Based on that, you can answer this question. So ninth is select the suitable resistance network used for 3-bit 12 letter DAC. Let V naught is LSP. So we have to choose R12 letter, that is 3-bit, and V naught is LSP. Okay, this is LSP. So we have seen that in DAC circuit, see in this the last part is 2R. Okay, so if we compare like this, so so basically we have here like R is 1K. We can understand this normally, that R is 1K and 2R is 2K here. So based on that, this is not having 2R at the end. This is also not having. So this is having 2K, and in between we have R. So this is fine, this is fine, and this is 2R, 2R, 2R. If you can see there, between R and here perpendicular branches we have 2R. So I think this also, you can answer this question then. 10th. So compute the value of current I for the given circuit. So in this question, they are saying, okay, this value of current of I. the value of I we have to calculate. Okay, so how we'll do? So it is like for these kind of questions, we can simply go with the Thevenin equivalent circuits, because if you try to apply these this direct formulas which I have, which like normally it is there, then there will be like difficulty in getting the solutions for this, because the those formulas are based on the standard circuits or standard configurations for DAC, but sometimes we can like those configurations can change, so it's better to go from the Thevenin voltage side concept. Okay, so this one is so let's say we have 0 volt here, RR here, so it will be like so we have, so this is basically 2R, this is 2R, and this is grounded. This is if we say that we have to see Thevenin from this side, VTH, and same as like RTH from this side. So how will solve? So for RTHs on for like Thevenin, I think you would have studied this thing. So RTH we are basically we can solve by grounding all the input source voltage and open circuiting the current sources. So here only we have the voltage sources, so we can like make this also grounded. This is R, this is 2R, this is R, 2R, then this V will be grounded to calculate RTH. This is 2R. Okay, so from this side we are calculating RTH. So this will be this simple R. This parallel configuration will be 2R parallel to R. This is R. Then in series with this R, so that is 2R. Again a parallel configuration with 2R, so it will be R. Then again 2R, then R. Then finally we will get this. This is 2R. This is R. And what is RTH here? So this will be basically equals to 3R. Okay, so this we got as 3R. Now we have to calculate VTH. So VTH is uh, we have this 2R here, we have 2R, this is there, then R, this is 2R, and we have a voltage source VB, this is R, this is grounded. So we have to calculate the Thevenin voltage from this side, VTH. Okay, so if it is 2R is here, then it does not matter because this is an open like open end. So we if we want to like if we don't want to like write this 2R, then also it is fine, because VTH will be like from here only. Okay, so this we have. So in order to solve this, so this will be what parallel, so it will be R, then this will be what 2R. So we have this thing here, 2R, 2R, V, this one is R, this one is 2R. Okay, this is VTH which we want. So so you can like there are a number of ways to solve this. So for me, I find like a current source to current conversion, because nodal I make mistakes. This simple, I can convert it into current source and then again back to voltage source. So using that, what I will do, this will be like V by 2R current source, and a resistance 2R will become parallel to this current source, and this is 2R parallel again, so it will be R. So we have R here, we have 2R, this will be VTH, then again this will become, so yeah, V by 2R, so it will be V by 2, this voltage, we'll be having this r will come in back to series in like series it with this r, so it will be 2r, this will be 2r, this will be plus minus vth. Okay, so it's simple voltage divider if we use, so here the voltage will be v by 2 by half. Okay, because this is 2r, this is 2r, so we are getting half, like half of what we have as a source, so with this will be v by 4. So now yeah, so now we have v by 4 here. So in finally where I will write, I will write it here. So we will have something like this is v by 4, we have 3r here, we have r here, and this one is minus plus. So the current, we can easily calculate the current flowing from here in this branch will be the current from here. It will be the same current, and then I will be v by 4 divided by 3r. So it will be v by 12r. Okay, so based on that you can solve, like answer the question. So whenever you, in short, whenever you get these kind of questions where you have been given these inputs from this, so try to go with thumbnail. It will be safe, it will be safe if you go like that. So there will be less chance to commit mistakes if you go directly with the formula. So that's why, so I will be this. Okay, so any questions in this? Okay, so I have some, let's say this week 11. So I have some extra questions which I will be giving the solutions. It can be helpful in your exams. So extra. So later also you can like refer to these extra questions, because I am recording this session, and you can then you can see this. I will suggest you to practice these questions, because it will be helpful in like solving questions in your main exams. So yeah, so based on that you can, like it will be good to solve these questions. Okay, so first question: full scale output of a digital to analog converter is 20 milliampere. The resolution is 80 microampere. Then the minimum number of bits required and percentage resolution are. So they are asking for the number of bits which will be required for getting this much of resolution, and they're asking what will be the percentage resolution for this. Okay, so we have this analog converter that is 20 milliampere. So we have free full scale value, and we have resolution of 80 microampere, so which is given by the formula VSV divided by 2 to the power n. So we have 2 to the power n equals to 20 milli by 80 micro. So if we solve this thing, wait, I have the answer. Yeah, so if we solve this thing, so it will be so we'll get n approximately 8. So we got like so we can say that for n equals to 8 bits, we are getting a resolution of 80 microampere when we have a full scale value of 20 milliampere. Now, percentage resolution, as I said earlier also, it is given by resolution divided by the full scale value VFSV into 100. So we have resolution as 80 micro divided by VFSV is 20 milli into 100. So we'll get this as 0.4% of resolution. Okay. Next question. Just read this question. So we can do one thing in this question, that is like either we can calculate the Thevenin voltage or the and resistances from this side, or we can step by step go from this side, come from this side. So I will tell you the both of the approaches to solve this question. Either like yeah. So coming from this side, like calculating the Thevenin voltage step by step of these parts is easy, but yeah, it is easy, and from here also it is easy only, but it depends on you which way you want to solve that. Okay, so we'll go with first calculating the full Thevenin voltage. So for that will be this one. Okay, so we have a circuit like this. I'll add some page in this. Add. Okay, so then we have this. So when we are calculating RTH, then we'll be grounding all the voltage sources. So this will be grounded, grounded, grounded. We have 2R here, 2R, 2R, R, 2R, R, 2R, 2R. Okay, so then this is parallel, which will be R. Then in series relations R, that is 2R. Then again parallel R. Then again 2R. Then R. Then 2R. Then R. So finally we will be getting this thing, 2R, R, RTH. So RTH will be 3R. Okay, easy. Now we have to calculate VTH. So for VTH, we'll just draw the circuit again. This is V, let's say 1.6 volts. We are taking it as V. This is 2R, 2R. We have one resistor here, R. Yes, we have then 2R. Then we have R, 2R. Again, this is some potential is there. R, 2R, and since we are calculating Thevenin voltage, so this last 2R is not necessary. We'll simply see from this side. Okay, so so to solve, I will use this current to voltage voltage to current source conversion technique. You can use nodal, whatever you want, you can use that, whichever you find it easy. Okay, and whichever way you find it easy, just to calculate the Thevenin voltage. So for me, it will be uh, first it will be like these two will come in parallel, it will become R. This will convert into current source, it will be V by 2R. Here it will be R, it is 2R, R, and yeah, this will be 2R, this is V, this is R, 2R, this. Okay, so now yeah, so we got this R. Then again we'll come back to the original. So this will come in series with this R. So it will be 2R here, 2R, R here, 2R, V, R, it is 2R here. Okay, so this will be what? So multiply V by 2R multiplied by R, it will be V by 2. Okay, now again we can convert it into current, and this will be parallel. So and then again we'll come back to this R, like convert again back to this voltage source. So finally it will be V by 4. So it will become V by 4, it will be 2R. Now we have this 2R, here it is V, R, this is 2R. Okay, so now so then yeah, so we can do that same approach again, and then it will be like this 2R in parallel, it will be R, and we'll have to add these current sources, and then finally convert it back to voltage source. So it will be finally V by 4, 1 by 2 plus V by 2. This will be the current, this will be 2R thing, because this will become R, and this in series with this will become R. So here VTH. Okay, so this will be, and this will be equal to 5V by 8. So VTH will be what? 5V by 8, half of 5V by 8, that is 5V by 16. 5V by 16. Okay, so VTH is this. So now we got VTH, and now we already have RTH. This one we have VTH. So the final circuit will look like this. This will be 3R. We have 5V by 16. We have this one. Okay, this one is what? R. This is R. Yeah, no, this is 3R. Okay. So this is 3R. So we'll be having the current as I. This current will be same as here. So it will be I equals to 5V by 16, 1 by 3R. Okay, so now we have to calculate in this in this question what we have to calculate. We have to calculate the output voltage. So this will be multiplied with the feedback resistor 3R. So we'll get 5V by 16 equals to V naught minus. Okay, so yeah, and we are having 1.6 as value, so it will be zero point 0.5 minus 0.5 volts. Okay. So now, yeah. So basically, I was telling about this question. So when you have like consider the circuit shown with an ideal op amp, the output voltage V naught is dash volt. So when you have these kind of questions, you can simply go with the Thevenin and the Thevenin voltage and the Thevenin resistance, like Thevenin voltage and the Thevenin resistance, and then you can solve this question. Uh, so now I was telling you about the approach of when you have this, when you have to like use the Thevenin from here. So what if we use Thevenin from step by step from the second approach, if we talk about from the starting. Oh, so for the starting, Thevenin will be what? For here only. So if we just erase this thing, if we talk about Thevenin from here, then it will be the Thevenin resistance is R and Thevenin voltage is what? So if we have, if we see this circuit, it will look like this. This will be 2R, 2R. This is 1.6 volts, and we have to see the Thevenin from here. So this will be what? This will be V by 2 if we are considering this as V. So this will be V by 2. Okay. We have this now, this resistance R here. Then this is 2R. This is R. Okay, sorry. Yeah, and so on. So then we'll have to use the Thevenin here. Then it will be the resistance will be R. This 2R is parallel in 2R, this one. So it will be R. We have this resistance here, R, and the voltage will be half of this V by 4, because it will be like drop from this to this, so it will be V by 4. Okay, this is V by 4. Then so we have R is this one. So now after that we have again this 2R, a V voltage, and R, and so on. So now again we'll go like from Thevenin from here. So it will be what? So this is 2R, this is 2R. So we'll be having R as Thevenin resistance, and the voltage will be so for this I'll make circuit here. It will be like this is 2R, this is 2R, V by 4, this is V only. We have to get the voltage output across here. So if we simply like this is like, if we simply like use the current equation, then we'll get the current and we can find the VTH here. So it will be so the current will be V by 4 minus 4 Ri minus V equals to 0. So I will be what? uh, this will be minus 3 by V by 4 minus 3V by 4 into 4, I think, sorry, this will be plus, we are going in this direction, so this will be 5 V, so it will be 5V by 16 R I. So based on that, the VTH will be what? VTH will be equal to minus 2R I, that is 5V by 16R plus V. So it will be R, this is 8. So V minus 5V by 8, it will be 8. So this will be 3V by 8. VTH will be 3V by 8. This will be 3V by 8. Okay. Yeah, and then we'll be having this all till this v1, and then we'll be having this 2r here, 2r here. This is grounded, this is grounded. So here, like this is going to the op amp. So here we can get it is as like 2 by 3. So there the voltage will be this one 2v by 3 into 3 by 8. So it will be v by 4. Okay, some mistake happened. Wait, I think we have done some mistake here. So if we just clear this. So here like this. So we had this one. Okay, so we can do one thing. We can use the current source and voltage source transformation, and we can get this as 5v by 8. Again, this 2r resistors will be there because this will be r to r parallel, and this resistance at multiplication this will be 2r. We'll get 2r here, and this is going to op amp. So finally, after this, like this voltage will be what? So then if we solve this, then again the Thevenin, if we use Thevenin VTH and RTH here, VTH and RTH here, then it will be like R 3R. RTH will be 3R, and this will be 5V by 16. Okay, and this is grounded, this is minus plus, this is 3R, I think. Yeah, this is V naught grounded. So you can solve that from this way also. So basically either use Thevenin from the this side or Thevenin from each and each step, each by each step, and then also like you can calculate the final answer based on both of the uh, approaches. So this is, so next question. Okay. Yeah. So this question is saying an 8-bit unipolar digital to digital converter, that is digital analog converter, all analog output values are positive, has a full scale voltage range from 0 volt to 7.68 volts. If the digital input code is this, the leftmost bit is MSB, that this one is the MSB, then the analog output voltage of the DAC rounded off to 1 decimal places. So I think this is also simple. We are given the range, we are given the n bits. So we'll see. So n equals to 8 bits. Range is 7.68 minus 0 volts, which is 7.68 volts, which is equals to V full scale range. Okay, this is full scale range, and then we are then the analog, so output voltage. So this VFSR into 8 bits we are having, so this will be based on this. So this is 1 0 0 1 0 1 1 0. So b1 is this, b2, b3, b4, b5, b6, b7 and b8. So since this is 8 bit, so 8 bit. Okay, so based on each and every coefficient, so these are basically coefficients. So b1 will be 1 into, so it will be 1 into what, 1 by 2 plus 0 plus 0 plus 1 into 1 2 3 4, 1 by 2 to the power 4. Okay, plus 0 plus 1 into 2 to the power 6 plus 1 into 2 to the power 7 plus 0. And we know that what is the VFSR value, that is 7.68 divided by this. So this will get as 8. It will be to the 4, 6, 7, and yeah, it will be 4.5 volts. So the output by giving this much of input is 4.5 volts V naught. Okay, now the next question. A 10-bit D to A converter is calibrated over the full range from 0 to 10 volts. If the input to the D to A converter is 13A in hexadecimal, the output is dash. So if we see, we have one DAC, that is digital to analog converter, and equals to 10 bit. Range is given as 0 to 10. That means V full scale range will be 10 minus 0 is 10 volts. Okay, so now earlier the input was given as what? This binary form. Now the input is given in hexadecimal form. So basically what we are doing in the previous this question, we are converting this binary into, this is basically what, this is decimal. Okay, this is a decimal form. So basically we are converting the binary into decimal so that we can solve this, the output of this DAC. So here, like instead of binary, it's just given that it is hexadecimal, that is 13A. So the input is 13A. Okay, so if this is the input, then we have to first convert it into decimal. So the output equation will be same, but not completely same. It will be VFSR into the decimal equivalent of input. So this is the main equation. So instead of hexa, if something else is given, we have to convert it into decimal. Okay, so 13A will be what? This A is 10. So 10 into 16 to a 0. This 3 is 16 into this one. And this one is 16 square into 1. That is 314. Okay, it's because A is 10, 3 is 3 and 1 is 1. So we got 314 as decimal, in decimal form. So V naught will be what? VFSR we know 10 into 314. So one mistake, this is basically resolution. Resolution into decimal equivalent of input. So we will be having 10 to the power 10 into 314, which is 3.069 volt. So this will be the output for this equation. Now next question. Yeah, we have 1, 2, 3, 4, 5, 6, 7 questions more left. Yeah, next question. Consider 4-bit D2A converter. So we have a 4-bit D2A converter. The analog value corresponding to digital signals or values 00 to this one are 0 volt in this one. So okay, respectively. Then an analog value corresponding to the digital signal, this one is what? So we have basically uh, we have to find the analog signal corresponding to the full scale value. That is one. That is the full scale value. Okay, so we have a 4-bit DAC, one thing. Second thing is that for 000 we have 0 volts. Okay, for 0001 we have 0.0625 volt. Okay, so then we know that there is an increment of 1 bit here in the LSP, not in the middle bits and not in the MSP. So that is the 1 bit increment, and the increment in voltage is this one. So this is also step size. The minimum, like the minimum step it can take, that is this one, step minimum step size. And the other name for this is resolution. So like in short, they have indirectly given the resolution for this tag, for this 4-bit tag. So we have resolution as equals to 0.0625 volts. Okay, now uh, okay, resolution is given. Then resolution is what? V full scale value or range divided by 2 to the power 4. So if we multiply this with this, 5 into 2 to the power 4, we'll get V full scale range. And the output then is given by 0.0625 into 2 to the power 4 into 1 by 2 plus 1 by 2 square plus, okay, this is there. So uh, based on this, we have this. Hmm. Yeah, I think this will come same as, yeah, okay. So you can calculate the V full scale full scale value. Or wait, basically V full scale a bit. So since the input, the lower limit is 0 volts, so we can get full scale from here itself. V full scale value will be, so this is range basically, so this will be V full scale value so V full scale range is V full scale value minus 0, because 0 is the minimum value which they have given. So V full scale value will be V full scale range, that is 0.0625 into 2 to the power 4. Okay, next question. In the digital to analog converter circuit shown in the figure below, VR equals to 10 volt and R equals to 10 kilo ohms. So we have to find the voltage V naught. We'll find this I also. Okay. Yeah. That. So in this question, yeah, so okay. VR is given as 10 volts, R is 10 kilo ohms. Okay, so how we'll solve this? This is basically, if you see, it looks little difficult, but it's very simple. And we know that this is 0 and this is maintained at 0 volts. So basically this is, we can like separate also and we can see. So if you see like this is grounded, this is grounded. So this is what? R. Okay, 2R parallel to 2R, this is R. Again we have R in series, so that will be 2R. That then again it will be what? Parallel to 2R, that is R. Then again R, so it will be 2R. Parallel to 2R it will be R. Then again this 2R. Okay, so basically we can say that we have 2R here, we have 2R here, this is VR. So in short this is this. So if we have a current, let's say this is the current in this branch will be what? VR by 2R. So the same current will go through this VR by 2R. Okay, so if we expand this, it will be basically, and if we see in this circuit itself, VR by 2R, VR by 2R. So since we have seen for this, like each and every ladder, or we can say this is since R to R ladder, for each and every ladder we have the, like the circuit which is at this side is same as that of circuit which at this side. So we can use similar approach, and this, what we can do, we can uh, we can divide the current equally into both the branches again and again. So this will be VR by 4R, this will be VR by 4R, this will be VR by 8R, this will be VR by 8R, this will be VR by 16R, this will be VR by 16R. So one thing we got, this I equals to VR by 16R, which will be 10 divided by 16 into 10k. There will be 62 point something, some 62.5 microampere maybe. This will be this. Okay, this thing. Then this. So now we need this V naught output, na output voltage V naught. So V naught will be what? So this will be the current from this side and the current I1, I2. So V naught will be minus I. This is, let's say, I3, I3 into R. So I3 is what? I1 plus I2 R. So this will be, I1 is what? VR by 4R plus VR by 16R into R. Okay. So this will be 4, 5 VR by 16 minus 5 by 16 into 10. So we'll get like 3 minus 3.125 volts V naught. Okay. So we have seen two types of questions like this, like one this R to R ladder, and another one was this one. This is also R to R, but thing is that here there were two voltages in between. So it is difficult to like use this approach which we used just now, like dividing the current into both of the branches as they were looking same, because here like each and every ladder is having the same is on the same ground potential. So based on that we divided the currents in both of the branches and we solved that easily. but this you will have to be careful when you are solving, because this cannot be every time this approach you can use that. So yeah, that's why. So you can here also go with that Thevenin and RT, like R Thevenin and voltage Thevenin approach. But then it will be like you can also see if the question is being solved through easy process, then you should go with that. Okay. So this question is done. Okay. Then our next question. So it is saying a digital system is required to amplify a binary encoded audio signal. Okay, binary encoded audio. So some okay, the user should be able to control the gain of the amplifier from minimum to maximum in 100 increments. The minimum number of bits required to encode in straight binary is. So here basically there is an audio signal. So there is a digital system also, and this audio signal is being encoded. That is, it's being digitally, like it is formed into like a digital signal kind of thing. So it has been encoded. So it is saying binary encoded audio signal is required. So audio system is required to amplify binary. So this encoded signal is given to this digital system, which is amplifying this thing, amplifying, acting as an amplifier. So it is basically amplifying this digital signal. So this is a digital signal. Okay. Yeah. So the user should be able to control the gain of the amplifier. So here there is some gain. The user has to control it from the minimum to maximum of. So this gain is 0 to 100 increments, like 0, 1, 2, 3, and so on. He or she can increase this gain. The minimum number of bits required to encode in a straight binary is. So they are asking for the minimum number of bits. So for 100 increments, if we want, like so we need at least 100 levels for this for our digital system. So that means basically 2 to the power n should be greater than 100. So if we use our DAC as, or this digital system as, like having 2 to the power n bits, which is greater than equal to 100 number of increments, then n will be greater than equal to what, 7. So that means at least we should have 7 number of bits so that we can generate this 100 increments in this digital system. If we go beyond and also, then also we will be having 100 increments. We'll be having, I think, yeah, we'll be having more than 100 increments, but the resolution will be better than this case and greater than equal to 7 case. So this is the one thing. Okay. Uh, so I think, yeah, this is also fine. Then the next question is, yeah. So this question is based on weighted register DAC system. So circuit is shown in the figure, which is a 4-bit DAC. So it is given that it is a 4-bit DAC. Okay. So we have R, 2R, 4R, and 8R. And the question is, the input bits 0 and 1 are represented by 0 and 5 volt respectively. Okay. The op amp is ideal. This op amp is ideal, but all the resistances and the 5 volt inputs have a tolerance of 10%. So the resistance is having a tolerance of plus minus 10%. Voltage sources is having a tolerance of plus minus 10%. The specification of the tolerance of the DAC is, so they are asking for specification of the DAC. Specification of the DAC. Okay, so we need to find out this thing. So how will solve? So this thing, like we can solve using, like we have R as plus minus 10% of R, which is basically uh, r greater than equal to zero point 0.9 r less than equal to 1.1 r. Okay, one thing. And we have, since the voltage value is 5 volt or 0 volt, so for 5 volts, 5 volt plus minus 10% of 5 volts, which is basically, mm, 5 volts, it can be greater than equal to 4.5 volts and less than equal to 5.5. So it will vary between these values. This is voltage, this is resistance. Okay, so now we notice what we have: the formula vf full scale value, and we have rf IR standard formula, and we have b1 to the minus 1 plus bn to the power minus n. So now this both are having tolerances, and this voltage is also having tolerance. So we need to find the maximum, the specification for the tolerance of the DAC. So V naught max can be what? It will be uh, like the maximum tolerance. V naught max tolerance can be what? So the maximum tolerance of voltage, that is 1.1 into maximum tolerance of the resistance 1.1, and this, the resistance at the denominator, it should be minimum, like the tolerance should be minimum for that, that is 0 0.9. So then in that case this will be maximum, so this will be what? 35%. Okay, so this is the maximum tolerance which we can achieve from using these resistance of these tolerances. Okay, now the next question: what is the resolution of digital to analog converter DAC? What is the so they are asking for the definition of the resolution. So it is the comparison between the actual output and of the converter and its expected output. Okay, it's deviation between the ideal straight line output and the actual output of the converter. That is, I think, what we say, gain error, maybe. Yeah, it is smallest analog output change that can occur as a result of increment of the digital input. Then this is, I think, correct, because smallest word is there. So smallest analog input change which we can get from an increment in the digital input. So that is like resolution, the definition of the resolution. So let's see the last option also. It is its ability to resolve between forward and reverse steps when sequenced over its entire range. No, I think this is not. It is a measurement between the output and output. No, this is quantization error, or we can say simple error. Yeah, so this is fine. Next question. The difference between analog voltage represented by two adjacent digital codes or the analog step sizes. The thing this also same step size, the difference between two adjacent digital code, that will give the step size, and step size, as I already told you, that is the resolution. This is resolution. So what is the major advantage of R2R ladder digital analog as compared to binary weighted? So we have seen in R2R as compared to binary weighted, they use only two resistors. So what is happening because of this? Since two resistors are there, so these resistors are having tolerances in practical world. So it will create issues when we'll be realizing our DAC using multiple values of resistances, because each one will be having their own tolerances and we cannot get precise solution from that. So to avoid that, or like to reduce that thing, we use only two type of resistors, that is R and 2R. So that helps in making this drawback, like for the drawback of the binary weighted digital to analog converter, to solve that drawback. Okay, so these were the questions. uh, so we'll just recap fastly. So we talked about data, like digital to analog converters, and the output equation of that, like how the output equation is given for that. And then we saw that the the main like main significant bit contribution to the output and the least significant bit contribution to the output also. Then there is some dynamic range concept, but we don't have to look more into this. It's just for the information. Then we saw that basically what this stack is. So we are giving a digital inputs, let's say b1, b2, b3, and they are in form of either 0 or 1 as shown in this axis, and we get output from this. uh, these outputs are based on the number of bits which we are using. So here, like, we have used 8 bars, that is n equals to 3 bits, and this is the transfer characteristics of 3-bit DAC. And we also saw this resolution is given by this, is also called as LSB. So we saw that higher the end, finer will be the resolution, it will look more continuous, but at the same time it will become costly and complex. And then we came to know about two type of DACs, that is one weighted register DACs and R2 or ladder DACs. So weighted register DACs, they use set like resistances in multiple of twos based on the number of bits. And we saw their equation and the drawbacks, like they can have the gain error and offset errors, and they can have like dynamic error also, but we didn't discuss. If you talk about static errors, gain error and offset errors, we can nullify them. Gain error can be nullified by adjusting RF value, and the offset error can be nullified by trimming the V offset voltage. And the major drawback of this weighted resistor is that we are using multiple values of resistances which are having different tolerances. So the precise value, we cannot get like precise output from this weighted resistor DACs. Then we came into R2R ladder circuits, and we saw the current mode of that, because here we were getting the current and how it is working. So this was the output equation, and we saw some extra questions. So this you can refer for your like exam preparations, and we also solved the assignment questions. Okay. Yeah. So yeah, if that is okay, so then so I think yeah, that is fine. So we'll end this session today. Yeah. Thank you.